meet Lalit Vaishya from Harishchandra Research Institute. He will be speaking on sign change of Fourier coefficients of normalized Hecke eigenforms at primitive binary quadratic forms of fixed discriminant. Okay, Lalit, you can start
Okay,
now.
thank you, ma'am. And first of all, I would like to thank the organizers for giving me opportunity to speak here. So my title of the talk is sign change of the Fourier coefficients of Hecke eigenform at the primitive binary quadratic forms of the fixed discriminant. So here is my outlines of the presentation. So some history and basic things about the modular forms and the main results, and then a brief proof. So the sign change problem is one of the interesting problem in number theory, which has been studied by many authors. And there are the many results which deal with the quantitative results, such as the number of signs for the sequence of the Fourier coefficients. So when you consider the subsequence of the Fourier coefficients, then the problem becomes more difficult. So uh, we assume let f be an Hecke eigenform. So normalized means that the first Fourier coefficients lambda f1 is 1, and this normalized means we have removed this n to the power k minus 1 by 2 from the Fourier coefficients. So in 1985, this Ramurthy have studied the sign change property for the subsequence at the prime numbers. Precisely, he considered that lambda fp where p runs over all the primes. And in 2013, Knopp, Conan, and Wilkinson shows that if the Fourier coefficients of the cusp forms are reals, then there are they changes the sign infinitely often. And in 2013, Jaban Meher, Kashi Vishwanath, and Karamdev Shankar studied the problem for subsequence lambda f n to the power j, where he considered j equal to 2, 3, and 4. And in 2014, Conan and Martin shows that if you consider the subsequence lambda fp to the power jn, then there are infinitely many sign changes for almost all the primes p and natural number j. So recently, Somaru Banerjee and Manish Kumar Pandey considered the similar problem for the sign changes for the subsequences, which are the sum of two squares. And precisely, he proved that there are infinitely many sign changes. So if k is an even integer and f is a normalized Hecke eigenform for the full modular group of weight k, then the sequence lambda f c square plus t square have infinitely many sign changes. And he proved that in the interval x to 2x, the subsequence lambda f c square plus d square have at least x to the 1 over 8 minus 2 epsilon many sign changes. So we have considered, we'll show that the problems, the theorem can be improved, and this method, whatever this Somiru Banerjee and Manish Kumar Pandey have used, can be extended to prove more general results for the positive definite binary quadratic forms. So let Qx denotes a primitive integral binary quadratic form defined as a ax square plus bx1 x2 plus c square, where this a, b, c are the integers with co-primality condition and with the fixed discriminant d, which is defined as a b square minus 4ac, and which is negative because q is a positive definite. We have considered q to be the positive definite quadratic forms. And we know that the generating function theta q defined by uh, summation of all the tuples in z square q to the power qx, uh, which is, if you write the Fourier expansion, it becomes rqn q to the power n, where rqn denotes the number of representations of n by the quadratic forms qx. So we know that this theta qx is a modular form of weight 1 for the level gamma 0 mod d and the character chi d. This character is defined by the Jacobi symbol, which is the extension of Legendre symbol, and precisely the formula for RQN given explicitly in terms of the character, which is given by WD times the summation over the divisors chi d over d, and WD is a constant according to as d. And we will see from the formula that this RQN does not depend on the choice of A, B, C, but it depends only on the choice of only on the discriminant. So Now we'll start some little bit about the modular form. So let SKL chi denote the space of cusp form of weight k for the congruent subgroup gamma 0L with Dirichlet's character psi, and F is an Hecke eigenform, a normalized Hecke eigenform in the space SKL chi with this Fourier expansion. So uh, this normalized means this lambda f1 is 1, and this lambda fn we call it the nth normalized Fourier coefficients of f, and precisely this lambda f satisfies this recursive relation due to Hecke, which says that lambda fm into lambda fn is equal to summation over d dividing d divisors over the GCD of m and n psi d lambda f m square mn divided over d square. So whenever m and n are co-primes, the coefficients are multiplicative. So precisely this lambda fn satisfied this Delink's bound, and we'll assume that the Fourier coefficients of reals, because uh, uh, it is not necessary that the Fourier coefficients lambda fn's are always real. So with this assumption that the lambda fn coefficients are real, we'll prove our results. We'll state that if f is an Hecke eigenform and the Fourier coefficients of real, then the sequence lambda fqx, this is a binary quadratic forms defined earlier, then this subsequence has infinitely many sign changes. And precisely we prove that in this interval, at least x to the power 1 by 5 minus 2 epsilon, many sign changes. So to study the behavior of sign changes, we need to consider the following two sums, two partial sums S1 and S2, defined over lambda f q by qx, where x removes all the tuples and up to x. So this sum, we can write it as a lambda f rqn. So if you write n equal to this one, then this lambda n repeats rqn times. So similarly S2. And this rqn is the number of representations of n by qx. So it is enough to consider uh, the upper bound for S1 and the approximate behavior of S2. So precisely we'll prove the following proposition. Let's state that S1 has the upper bound of order big O of x to the power 3 by 4 plus epsilon, and S2 have the approximate behavior, which is c times x plus big O of x to the power 3 by 4 plus epsilon. And this c constant is positive and depends on the uh, cusp form f, epsilon, and d. So to prove this proposition, we'll use the truncated parents formula, which relates with this partial sum with the L function. So we'll define the following Dirichlet series RF theta q, which is defined as a lambda fn rqn over n to the power s, and this appears in the Rankine-Selberg convolution. And this is we define another Dirichlet series, and we'll decompose these Dirichlet series into the known L functions. So precisely we'll prove the following lemma, which relates this Dirichlet series RF theta and RS with these known L functions. And PS is given by the PS, and this US is given by the Euler product, which converges for real part of S uh, bigger than half. So, to prove this proposition, to prove this proposition, we'll use the following key ingredients. The first one is truncated Perron's formula, and then the convexity bounds for L functions, and the integral moments of the Rankine-Selberg L functions. So this is the truncated Perron's formula, which relates the Dirichlet series uh, and the partial sum. So we'll state that under certain conditions, this partial sum is equal to 1 over 2 pi I, the integral from b minus it to b plus it ds over x to the s plus over s ds, and the big O things. So whenever this an satisfies the Ramanujan-Peterson conjecture, that is the big O of n to the power n, then this factor dominates over this one. So precisely we'll have this truncated appearance formula. And we'll use these two key lemmas, which is the convexity bound and the mean square estimates for the Rankine-Selberg functions to prove our results. So this convexity bound says that if you have any L functions of degree D, and then uh, s minus 1 over s plus 1 to the power r lf sigma plus it is of order 3 plus sigma plus it to the power d times 1 minus sigma by 2 plus epsilon, and this R denotes the order of pole at s equal to 1. So if L is entire function, then R will be 0. So, and this lemma due to Matsumoto, which state that if F is an Heike eigenform, sorry, this will be Heike eigenform, then the mean square estimates is given by the following estimates. So now we'll state to prove this proposition. We know that this the D-links bound for lambda fn is which says that this lambda fn is a big O of n to the power epsilon by 6, and this Rqn is the Fourier coefficients of modular form. So it satisfied the Wales bound. So together this we can have the order of an. So this says that this an is a big has the order big of n to the power epsilon. So we can take b to be 1 plus epsilon and apply the truncated appearance formula. So after applying the truncated appearance formula, we will shift the line of integration from 1 plus epsilon to 1 by 2 plus epsilon, and then apply the Cauchy's theorem, and then the estimates for the L functions, and convexity bound for this convexity bound for the L functions to get the estimates for this S1 and S2. So to prove the results on the sign changes, precisely we'll use this key lemma, which is due to Ramurthy and Jaban Meher, which says that if an is the sequence of a real number which satisfied following three conditions, that an is a big O of n to the alpha, and the partial sum n up to x, an is big O of x to the power beta, and the square of the partial sum is c times x plus big O of x to the gamma. Then if you choose delta bigger than alpha plus beta and gamma, then the sequence an has at least one sign change in this interval, and precisely in the interval x to 2x we have x to the power 1 minus delta sign changes. So since we have the estimates we have the estimates for S1 and S2, which is big O of 3 by 4 plus epsilon, and C the estimates for S2 is a C times x plus big O of x to the 3 by 4 plus epsilon. So we can choose the maximum of this epsilon plus 3 by 4 plus epsilon, the number bigger than this epsilon plus this one. So precisely we'll choose delta to be 4 by 5 plus 2 epsilon, and we'll use this lemma, and so that in this interval we have at least one sign changes, and precisely in the interval x to 2x we can have at least x to the power 1 over 5, that is 1 minus this 4 by 5 plus 2 epsilon, which is 1 over 5 minus 2 epsilon sign changes. These are the references that I have used to prove the results. Thank you. Hello.
Yeah. Thank you, Lalit, for such a nice talk.